Good afternoon and good morning. So this is Zhipeng Li. I'm a PhD candidate from Washington State University, and Dr. Xianming Shi is my advisor. So today is my pleasure to be here to introduce my research work. The topic of my presentation focuses on the effect of graphene oxide on the properties of flash-based geopolymer paste before and after physical damage. First of all, I'd like to briefly introduce the background. As it's well known that the cement industry greatly contributed to the global CO2 emission, and this kind of greenhouse gas will result in irreversible environment damage. So it's necessary to find something to mitigate the carbon footprint of cement industry. As a kind of supplementary cementitious materials, flash is a promising candidate. And in recent years, many research reported to use flash to propel silica-free cementitious materials. So this is called the geopolymer and is considered the most promising new generation cementitious materials. And in addition, flash is also kind of solid waste, so upcycling it is also sustainable and environment friendly. And flash was usually obtained from coal-fired power plant, and it looks much like the cement, and their chemical composition are also similar. So from the SCM results from the flash, many flash are in round form. So this is also people like to use it in cement industry because it can be used to decrease the friction between aggregate, and it can use it to decrease the demand of water, and it can also accelerate the hydration process. And so in our presentation, we'll focus on the alkaline activated flash geopolymer. So when flash meets alkaline, the alkaline starts to attack flash, and the positive ions inside the flash will exchange with the positive ions from the outside, and so the chemical bond will be broken, and then the flash will broken into many small units. This process we call it alkaline activation, also depolymerization, and then those small units will connect with each other and then generate new hydrates. For this process, we call it repolymerization. And so compared with ordinary Portland cement, geopolymer is more affordable and sustainable. But however, for many geopolymer composites, its early edge strength is undesirable. So to figure out this problem, we use graphene oxide to try to improve its performance. And here is the flash composition that used in this study. This kind of flash was obtained from Oregon. And this table provides the physical properties and some chemical compositions. We can find the chemical compositions is much similar to cement. So based on the roles played by this composition, they can be divided into two parts. The first one is network formers, and the second one is network modifier. Or this played different roles in the hydration process. This table provides the mixture design of the geopolymer paste. So this mixture design was obtained by a set of uniform experimental design, and we obtained many data and then optimize, and then we can get this mixture design that featured higher strength. And in our previous research work, we also developed a geopolymer paste, but in that paste, we use calcium chloride to strengthen the matrix. But this may result in some problems that the chloride may induce some rebar corrosion risk. So to mitigate this risk, in this study we use TIPA to replace the calcium chloride. Here we also use F500. F500 is a type of extinguish agent. So in this study, we try to use this one to envelope the free carbon particles. And based on the results, F500 works, and it can mitigate the bad effect of the free carbon particles. So this technology was also protected by the American patent. The main difference between these two binders is the graphene oxide. The first one, no graphene oxide. The second one contains 0.02% graphene oxide to the mass of flash. Here is the basic information of the graphene oxide that we used in this study. Graphene oxide is a type of nanosate. We can learn from this SEM results. Is a nanosate, and from this XPS results, we can learn that the main chemical component of graphene oxide is carbon in about 71%, and oxygen with about 27%. So to guarantee dispersion of nanomaterials is also an issue. So to guarantee the dispersion, we use ultrasonification combined with water reducer. So water reducer is a kind of surfactant. It's usually used to help disperse these tiny materials in water. And we tested the compressive strength of these two binders. And the graphene oxide did improve the strength, but the increased ratio is lower than many ratio reported by other researchers. So the main reason might be due to the difference of the matrix, and so many electron activators may also affect the function of graphene oxide. And we also run the compressive strength testing for these two samples at certain physical cycles. We can find for this blue line is the result of normal geopolymer. From this result, we can see that this geopolymer can only resist about 84 physical cycles, but for the geo-modified one, it can resist about 96 physical cycles. Is about 50% improvement. Here we also test the surface and the transport property of this geopolymer. First, we test the water contact angles, and we found after admixing graphene oxide, the water contact angle of geopolymer increased about twice. So for original one is about 15 degrees, but for the modified one is about 32 degrees. And the first stage water absorption coefficient was also decreased by 2 times by the mixing graphene oxide. So combine these three results, we can summarize that the graphene oxide induced a higher matrix strength, and it resulted in less absorbed water and result in less hydrophilic surface. So all these three change will result in improved freeze-thaw damage resistance. Here is the SEM results. From these SEM figures, we can find some beautiful hydrates. From the bottom two figures, we can see some beautiful layer-by-layer structures. But in original geopolymer, we didn't see such kind of things. Just only the flash particles and some cracks. But from these figures, no obvious cracks, and this layer-by-layer structure looks more homogeneous. And so I think the main reason of this result might be due to the template growth role played by geopolymer, also known as the seed effect, that provide a growth point, and the hydrates will grow on this point and then generate layer-by-layer structure. And then we run NMR results, and then we run NMR testing. And in this study, we only focus on the 29 silica NMR. Based on the structure of silica tetrahedron and their location and their frequency, so we can divide the silica structure into these 5 types. So from Q0, Q1, Q2, Q3, and Q4. And from this structure, we can see that with number increase, the structure becomes more complex. And in other words, the polymerization degree increased. So we can also use NMR to evaluate the reactivity of flash. For example, if in this flash, the Q4, Q3 is more dominant, then which means the reactivity of this flash may not very good. Here we run the NMR test for original flash particles, and this one is alkaline activated geopolymer, and this one is geo-modified geopolymer. And so here I didn't show the y-axis, but all these 3 figures are in the same side, so we can compare the height of these peaks to, have basic idea. And here I need to mention that these NMR results is a preliminary analysis. So, or this little peak, or this small peak under this black dot line is used to fade this dark dot lines. This dark lines is the original NMR result of flash. So here I developed just many small peaks to fade these dark lines, and then try to analyze the meaning of these different peaks. And so because this is a preliminary analysis, those peaks may miss, and some peaks may overlap, and some peaks may not reasonable. And yeah, I will refine this further after our next stage work. So based on this flash NMR results, we can say Q0, Q1 to Q4. And after alkaline activations, we can see all these Q increased. Okay, first let's say Q0 and Q1, or both of them increase greatly, maybe 2 times. For this part, for this result, we can attribute to the broken of flash. That means after attacked by alkaline, so the flash broken into many small parts. Those small parts. So for the increase Q1 and Q0 and Q1, we can attribute to the broken of flash. For this increase Q3 and Q4, we can attribute to the repolymerization of a small unit. After adding graphene oxide, we find the Q4, a more complex Q4 generated, and the Q1 decreased. So we can summarize that graphene oxide convert Q1 to Q4. That means make the hydration products more complex. This result was also confirmed by XRD that we can find some quasi generated here. And here we run the EDS results. We run the EDS analysis, and we found after adding graphene oxide, it increased relative concentration of calcium and decrease the relative concentration of aluminum. And it will also increase the Mohr ratios. So based on these two increased Mohr ratios, we can conclude from this equation that graphene oxide improves the polymerization degree. So this M is alkaline metals, and Z is means the polymerization degree. And here we compare the result, EDS result before and after freeze-thaw cycles. We can find graphene oxide. Yes. Based on these two results, we can find that the mixing graphene oxide will prevent the leaching of calcium. From these figures, before freeze-thaws and after freeze-thaws, in geo-modified samples, the change is not obvious, but in non-modified geopolymer, the relative concentration of calcium decreased by about 20%. So we can conclude this result to the negative charged graphene oxide that it will attract the positive charged calcium but repel the negative charged aluminum tetrahedron. Here is the summary. So graphene oxide improves the resistance to freeze-thaw damage of flash geopolymer. It can promote the generation of more complex gels, and it can also prevent the leaching of calcium under freeze-thaw cycles. This also helps to explain some other improved durability performance that's related to the calcium element. Future work, we will focus on improving the freeze-thaw damage of this geopolymer composite. And we will continue refine the NMR results. And first, I seriously thanks to Dr. Shi, who always supports me and provided me so many valuable opportunities to learn in WSU. Second one, I acknowledge the support from UTC and the trade dealers, and the 2020 David Gross Scholarship. I also thank Dr. Xu Gang and Dr. Scott and Dr. Williams for helping me in my work. Thanks. Any questions?
Professor Shar, do you have questions?
Yeah.
Yeah.
Very interesting and a good, well-organized presentation. One of the advantages mentioned in conclusion of adding GO was a reduction in, increase in resistance against freeze-thaw cycle. But that was certainly not very remarkable, and we know that air entraining agent and other could probably do better job. So right. What other advantages do you see for geopolymer in adding GO?
Right. Zhipeng, if you allow me, I will try to answer that. So first of all, yeah, the freeze-thaw durability actually maybe was not mentioned, but anyway, the test samples were really small. They were cement paste or geopolymer paste, and they didn't have any entraining agent. Oh. So that's why you don't see a whole lot of number of rapid freeze-thaw cycles. So, but once that's our next step. We're adding some water-resistant admixtures and fibers and air entraining agents. I think the performance will increase tremendously. And also, this is just cement paste, but when we test aggregate, I mean, when we test concrete, of course, with aggregate phase being in there, the performance will also increase. Now, back to your question, the real benefit of geopolymer, in addition to being environmentally sustainable, is I see one of which is reducing leaching. Zhipeng, if you could go back to one of the early slides, actually kind of implied that, even though you didn't specifically mention. Now, much earlier, there was a photo of FA plus Geo versus OPC. Could you go to that slide? I mean, in terms of leaching, that's basically visible. Yeah, this one. You can see the one on the very right-hand side, flash-based geopolymer with alkali activated, you have leaching, on the surface. But once you add the trace amount of graphene oxide, that leaching went away. Now, if we're talking about using this kind of cementitious material to lock up heavy metals, I think this is very promising because a 2D nanomaterial with a layered structure based on the conceptual design and also based on preliminary results, it will be really good in terms of chemically bind and lock up the heavy metals from the waste materials. That's one thing. The other one is, of course, the fire resistance. Geopolymers have been known to be providing better fire performance than traditional concrete. We haven't done much work on that, but I know there are people who have done similar work. Well, this geopolymer binder is different. I should mention, of course, that's why it was patented, because this doesn't really use any sodium hydroxide. This is just water glass, and originally calcium chloride, now TIPA and so on. So, well, maybe that's a very long answer.
Yeah. No, that's what with geopolymer. There is the issue with shrinkage. So, are you going to have any experience with shrinkage when you add?
Very good question. Very good question. Actually, I'm not sure why Zhipeng didn't represent that. In one of his published papers, this actually is intended to be serving as alternative to expansive cement. So in other words, this one actually expands a little, there's no shrinkage. And the level of expansion could be customized based on the mix design. So yeah, the shrinkage issue goes away.
Oh, very good.
Yeah.
Okay, thank you.
Thank you.